what usually is really helpful is you use this sort of tool is if you have sort of a general understanding of what do those tools actually do, what can they do, and what can they not do. And that's something that I would like to do in this talk, right? To sort of have a background, let's say, 2 semesters of artificial intelligence in 45 minutes. But actually to make you understand what AI does. And first thing is now, while you have a huge hype on AI now, AI is not new, right? I mean, AI goes back to 1950s, 1960s. And also a lot of the things that are now hype, like neural networks and chatbots, are things that go back to 50 years ago. Anyway, so those things are really old that we are now talking about. What happened is that in recent day, these things generated stuff that simply captures public attention. Generating fake movies of people, generating movies, answering questions, writing your papers. One thing I really like, maybe you heard it recently, there was this thing where there was a scam where people transferred 25 million from a company to an offshore account by simply doing a Zoom conference and inserting into a Zoom conference fake videos of the CEO, the CTO, the financial people, and essentially telling people to transfer the money, right? So this shows you AI is as Passan said, something that can empower people to do things they couldn't do otherwise, right? It's about human AI collaboration. Imagine, you could never pull off that scam without AI, right? How do you bring them to do that? So, and of course you see that this can be used for the good and the bad. And because of that, there was a lot of attention, like EU does a lot of stuff now, and I think, some things that come from the EU statements are confusing, but this is actually really good. They say 2 very important things. First of all, it's an extremely strategic technology. Anything you do is going to be impacted by AI. But the way we use the technology is going to have a huge effect of our everyday lives, right? And the reason this is so true is essentially twofold. The first one is AI is something like electricity, even today. Light is everywhere. Your phone wouldn't work without AI. Your car is driven by AI. The electricity distribution, the financial system, people who scam you of money, all sort of stuff is being done by AI. The second thing that you see is that in many cases, AI is not something that just incrementally improves things. It sort of fundamentally changes the way, transforms the way things are being done. Right? This famous thing about recently where there was a Beatles video that was created that was not there before. Right? It's not it helps you make music differently, like synthesizer in a computer. Essentially, it completely changes the field. You can just generate art, you can generate music, you can generate pictures, you can generate texts. It completely transforms everything. And one example I like actually comes from Albrecht, from your former PhD process. If you think, Tinder uses AI to create parrots, which means that essentially AI is going to fundamentally change the genetic composition of the human race in the long term. Right? It is exactly what is happening. So the impact is really huge. In many ways hidden. So, because of that, people have been, having a lot of fantasies and reacting to it in spectacular and utterly stupid ways, right? Like everything. So typically humans have loved to have fairy tales, good ones and bad ones, at the beginning of humanity. We don't have fairy tales anymore, so people believe in things like this. AI is going to take over the world. AI is going to make us happy and live without work for the rest of our lives. Both of those things being, and I want to show you, complete nonsense. And the reason it is so is the problem with AI, with artificial intelligence, is really in this term intelligence, right? As a human, you associate intelligence, I just quoted here some things from dictionaries, right? It allows you to think about things, gives you judgments, opinions, right? You think about intelligence, you think about philosophers, you think about scientists, something very, very human. And that is something that today's AI has absolutely nothing to do with. And again, quoting the European Union, when they were working on the AI Act, they actually provide a very nice definition of AI. AI is essentially a set of mathematical and computer science techniques and approaches. Right? It's a set of algorithms, set of mathematical methods that have certain methodology as it says in common, and that generate certain type of outputs, things like predictions, decision influencing, complex outlooks and complex situations. And further defining the AI, right, the annex, so they go and specify specific techniques, things like supervised learning, statistical methods, Bayesian estimation, logic. And that is the thing always to remember, because people tend to say AI, I just do AI, do it, right? We talk about AI, it talks about mathematics, nothing more and nothing less. And there are essentially two classes of AI methods. One is machine learning, the other one is more focused on logic, on symbolics. And what I want to do today is two things. First of all, give you a basic idea of what those methods are, right? So you use them, you understand what they do, what they don't do. Say what these new methods are, the advanced concept that you now see transforming AI, and especially talk about limitations and some things people are working on, right? So first of all, looking at the so-called symbolic AI, that was AI that first came into being famous more than 20 years ago, when IBM Computer beat Grand Chess Master. Already there, people were talking about intelligence machines and taking over our domain of intelligence. How does it work? And it's really interesting. Chess is a totally stupid game, right? You start on a board, you have a finite number of moves, and for every move you can answer with a new move, right? So you can go and solve chess by simply trying out all moves, right? There's nothing intelligent about it. It's just trying things. There's a slight problem there. There's actually something like 10 to the power of 120 of realistic things that you would like to try out. And to give you an idea of the size of the number, the total number of atoms in the universe is 10 to the power of 80. Right? So if you took every atom in the universe and used it to store a chess configuration, you still wouldn't solve it. Right? So that is what people always assuming is a very difficult game, and it's not easy to solve. But then, of course, you don't need to solve it all. So what the computers do is the following. They have chess experts who went there and formulated rules for judging configurations, right? So you see a configuration like that on a chessboard. There's simply a formula for calculating how good it is. And then using essentially this way of judging the quality of moves, the computer has algorithm for searching not every possible move, but searching on the selected moves which seem promising. And then the next thing is, to beat a human, you don't need to search the entire game. If you can look like 20 moves ahead, no human stands a chance, right? And that essentially is how the whole thing works. And in a way, that is how the first generation of AI, the thing that started with the IBM expert systems, really used to work. It is about three things. It is, first of all, having enough computing power, but then it is about encoding expert knowledge in a way that can be efficiently searched. Right? These chess programs, they did nothing spectacular. All they did was extremely efficient search on very fast machines, driven by a nice encoding of the chess knowledge provided by experts. Right? And this is my favorite statement about this, from Noam Chomsky, one of the original AI people. A computer beating a chess grandmaster is as fascinating as a bulldozer winning Olympic gold in weightlifting. Yeah, bulldozer can lift weights. Yeah, computers can search. Of course they beat human. What's the point? You cannot search faster than a computer. So there's really not that much to that. And one of the reasons why that branch of AI sort of run into problem is really about this encoding expert knowledge, which implies that you have experts who actually have the knowledge, and then you have the resources to actually encode this knowledge in rules that can be used. And you say, yeah, humans know anything, but imagine such a simple problem as face recognition, which AI does. You say, oh, I'm human, of course I can recognize faces. So I ask you, go down, sit down, and write a list of complete rules how to recognize faces so that a computer can do it. You're not able to put together that list, right? You know how you do that, but writing an algorithm that recognizes faces by telling the computer everything how to do is, which people didn't know how to do. And that was the limit of the original AI, and that is where the whole thing of machine learning comes in, right? That was a revolution that you had in AI, say 10, 20 years ago, when the machine learning came. So let me tell you how machine learning works, looking at image recognition, which is the classical machine learning technique. And that's actually an example of one of the the classical textbooks on AI. So you look to different type of fish, and you would like to recognize and differentiate between those fishes. So what you do is you somehow quantify what you see. You have to map what you want the computer to do onto numbers. Computers can only handle numbers. So you define somehow the width of the fish and the color. And then you take a huge amount of fish, and instead of sort of eating and selling them, you just measure them, and then you plot the size here in this graph, right? So you can see here essentially there's the width, there is the color, and then you can plot each fish here. And you see that there is a tendency that actually they separate here in this space, right? So if you go like this, then you will see that the one fish is on one side and the other is on the other side. And essentially, the entire thing of machine learning, face recognition, all the stuff that is done, goes down to the ability of the system to take data that is plotted in some sort of a multidimensional stuff and finding this function that separates what you want from what you don't want. Right? So you want the system to be able to find essentially this line that separates the fish based on nothing more than the data it has, and for every data point, the assignment of what the data point means. Right? You as a human look at it, you see this is the line. So how does the computer do that? Several things. First of all, you just try everything, right? The chess approach. You just plot every possible curve, and eventually, for every curve, you count the number of errors, and then you select one that produces the least errors. As usually, trying out all the possibilities is not a good idea, right? There's an infinite number of possibilities, and trying them is not an option. So how do you do that in a way that actually is computationally feasible? And that's where machine learning comes to play. What you do is 3 steps. First of all, you decide what this function roughly looks like. So we decided it's this sort of a, parabolic thing that separates it. Then you pick parameters which describe different versions of that function. So here, for example, it could be how big is the opening, where does this thing sit here, which way it is turned. Second thing you do, you define what is called an error function. You tell the system what it's supposed to do. What is the difference between the correct and the wrong answer? In this case, it's just being on the wrong or right side of that function, right? Being classified as a right or the wrong fish. And then you run something which is called like a numerical optimization algorithm. So essentially, you run those algorithms to try to estimate the values of those parameters in such a way that the cost here, this value of this function, is minimal. Right? The classical way, if you know something about optimization and computer and engineering, it's essentially called gradient descent. So you have here the error function, right? The higher the thing, the higher the error. And the point you look in which direction is the error decreasing, and you move your system this way. Now, the interesting thing is that there is no machine learning algorithm, be it GPT or whatever, that does anything else than that, right? Those things sound very complicated, because they are, usually, but in the essence, all that those algorithms do is these 3 steps. It's face recognition, it's playing some sort of games, it's GPT, it's video creation, whatever. Nothing else happens there, right? And just to give an example what it means, right? Imagine that you're talking about linear function. It's high school mathematics, right? So you compute f on x as a function a multiplied with x plus b. You've done some statistics. It's just linear function, right? So then your parametrization essentially is this a and b, and what you do is if you have enough data, you try to find this linear function in such a way that it's closest to your data by fitting a and b. Right? You've done any statistic on your data, you know it, right? What is it? It's essentially linear regression, right? And in a way, linear regression, which people have been doing for hundreds of years now, is just the simplest form of machine learning. And in a way, machine learning is really nothing more, right? You understood this, you understand machine learning. Now, of course, things are more complex. So instead of just having a times x, you can have a 1. You have 2 inputs. So then you have a 1 and a 2 that you have to learn. And you can have 3, and you can have d-dimensional, highly dimensional inputs, right? And if you encode that, you get something like a sum. But most important thing, if you want to take the sum and you want to sort of visualize what's happening, you enter a picture like this, right? Here you have your inputs. This is arrow x, right? Here you have the things, you multiply it, so you put them here on those errors. So every time something goes into the system, it goes over the error, gets multiplied with something, and now you have this thing in the middle that simply sums them out, sums them up and does something with them, right? And that is what you might have recognized, essentially, a simple neural network, right? And that's another interesting statement about neural machine learning. A lot of people say, this thing is somehow brain-inspired, this thing works like a human brain. And that is not really true. What is happening is, that is how machine learning works, right? This is the mathematical formulation. And then people realize that that mathematical formulation, inspired by things like linear regression, can actually be very nicely conceptualized in this graphical way. And then so, it's sort of a similarity to what you may have in a brain. But it's not like people took a brain and decided to build a machine like this, right? It's somehow, it's interesting that you have this similarity. If you go into neuroscience, you will see that it breaks down very quickly, right? So there's much more complexity there going on. But that is what a neural network is. And now, if you go a bit further, instead of having just one such a connection, right? You have many inputs here, and then you have this. You have here, this neuron. It's connected to every one of those inputs. And you have more of them and more layers, then you just take what you have been doing with this linear function, like linear regression, and just concatenate that. And once you concatenate it, you add one thing to it, which is you don't only compute those sums, but you add this little function here in the beginning, which is like a nonlinear function. It's usually some strange form, it doesn't matter. But it's absolutely crucial, because somebody went out and has proven the following thing. If you do this sort of a concatenation, two levels of this very simple linear functions in many dimensions, and you add the secret sauce, this function here in the beginning, then you can use that to compute any other function that you can come up with, right? So essentially, what this thing is saying is that by doing this sort of a mathematical structure, which can be pictured in the form of this neural network that you could say has something similarity with the brain, you can compute any function that actually you can come up with that is computable, right? And that is really interesting. Why is it interesting for computing? Because, of course, anything that a computer does is just computing a function. You ask a GPT something, you input a text, it's just an array of numbers, right? You get out another text, it's just an array of numbers, right? So you just compute a function. So that means that statement tells you that by using this structure, right, having this structure with those parameters, you can just do any computational program. You can just, anything a computer can do can be done. And which means that anything that a computer can do can be done by defining this function, defining an error function, taking your data, and fitting your parameters, doing very large linear regression at the end of the day. And the interesting thing is that all this stuff that you now see in this fascinating machine learning is just that. Right? There's absolutely nothing more there. Now, so in other ways, it's really important to understand. People will talk, these machines are somehow, they learn, they're intelligent, they can do things they were not programmed to. Machine learning is essentially just a way of programming computers. Instead of going then and writing code that tells you line by line what a system should do, you do it slightly differently, right? First of all, you specify what a system should do by two things. By providing it data, and by writing your error function, your loss term. And then you give a system a hint how the solution looks by picking this family of functions. Is it linear? Is it something crazy? Whatever. And picking a set of parameters. And then you go and take sort of an optimization algorithms. There are tons of them around, which of course has to work and fit. And you run it, and you hope that the system produces a solution. And there are many things in there. If there is no solution in the sense that the data does not contain enough information to do the optimization, the system will not solve it. If sort of the function that you started here with been parameterized, the system will also not solve it. And so it's a very important thing. When you use an AI system, saying just, throw the AI at it, it will do something, just doesn't work, right? The data have to contain the information. Your loss function has to reflect what you actually have to do, and then you will get a solution. But AI cannot create new knowledge in this sense. It just extracts knowledge, informs, and I think that is a very, very important conclusion here, because some people think of intelligence as, creating new knowledge. It doesn't. All it can do is take a big amount of data and extract from that data information about what are the optimal parameters to satisfy your loss function. You do wrong loss function, you lost. You take wrong data, you lost. So that essentially is, the very basic of AI. And some of the things why, what makes it difficult, why it's such a big research center, research team, because you'd say, the way I presented it, just linear regression, just some numerical optimization, why are we putting billions of euros into AI research, right? If it's so simple. And that is the old thing. Many things are extremely simple at the core, but are extremely difficult when you actually want to make them work in reality. And that is sort of the problem. And, first you could say, first of all, since you have proven that this very simple form of having just 3 layers here of neurons or having just this function can compute anything, that should be all that you do, right? Now, there's a slight problem with the whole thing. Again, you can, picture this thing as a vector matrix multiplication in the end. That's something that goes back to the title of the talk. If you know something about mathematics, you understand why it's just a vector matrix multiplication. But of course, the challenge is, I've shown you an example with one parameter. GPT-4 has, I think, 1.7 trillion parameters, right? So you're talking about estimating 1.7 trillion numbers, and you're talking about estimating them from petabytes of data, right? And what it sort of comes down to is this example. Imagine I threw you, I let you off at a random point on Earth and said, find Mount Everest. It's very simple. Everywhere you go, you just try to go up, right? Very simple principle. If I just drop you in a random point of Earth, you will never finish because it's non-trivial, right? So it's simple principle, it works, but given that huge amount of data, you need to find ways to do that. And that is essentially, what machine learning does, that people came to the fact that you do transformers, you do CNNs. I will not talk about how they work, but all they do is essentially finding structures in arranging those matrices, not just a single huge matrix. It's many of them connected in complex ways in such a way that you increase the probability of your optimization algorithms finally finding a good solution with finite data in a small amount of time. And again, think about it, 1 trillion numbers that you have to estimate from a petabyte of data. And the reason why machine learning and AI has taken off so in recent time is very simple. First of all, we got the computing power and the storage to do it. Second, we got algorithms that leverage that computing power to do something that approximately work. So we come to ChatGPT. I don't know who of you really knows how ChatGPT is trained, or at least roughly. And I think some people heard that. And the really interesting thing is what happens is ChatGPT, those models are trained a very simple way. They're given huge amounts of text. Then they're given a sentence, words in the sentence are deleted, and then your loss function is essentially, was I able to predict the words that usually be put in place, which I deleted? And then you just run your optimization algorithm. Right? That is how those things are trained. And then, of course, this optimization goes the way I told you. It uses exactly this notion of having vector matrix multiplication, and these parameters here in the matrix are the parameters you are trying to estimate, and you estimate them via numerical optimization by looking at how close you come here to the word. And it's not just a single word, because many sentences can be completed in different ways, so you look at probability and so on. So how do you generate all those beautiful texts and papers? Right? That's even simpler. Once you've trained the system to predict the most likely next word, you essentially give it a question, and then it predicts what is the most likely word after that question, which is the first word of your answer. And then you take that, feed it into the system, and you predict the second word of your answer. Now you ask, why does the system generate different versions of an answer? It's very simple. Because what it learns is not that there is always this word in a sentence, right? But there are different ways of completing a sentence. So you have different probabilities, right? So you can essentially go there, and depending, you can take the most probable thing, or you can take the less probable thing. And that is the reason why you can generate nearly an infinite number of answers to your question. But all it happens is applying the principle. I optimize per parameter to generate the next word. So that is what the system does. Now, once you understand what it does, you can actually look at what you can do with a system. And you talk about analyzing text. Let me give you an example. I actually had a discussion with a company that was looking at using it for contract analysis. So I gave him an example. I took a voucher I got for a car I rented somewhere, gave it to ChatGPT, as asked it to summarize the document. It actually did a really good job. You look at it, it was like a 20-page document, the legal thing, and extracted what has happened. It has the key things like location, it has driving license, it has a cost. It actually has this thing, waiver liability that I have to pay up to 1,000. So it really summarized it really well. I said, okay, let's see what it knows about the contract. So I asked it questions. So I asked it, if the car is stolen, what will I have to pay? It gives you a really good answer. It sort of can extract from the text the answer that if the car is stolen, you will have to pay this sum, essentially. And actually, it tells you that you need to have this amount available on your credit card so that it can block and everything. I did another thing, it's on a driver license, so could I drive the car with a license borrowed from my twin brother if I had one, right? It actually gives me a good answer. Again, it says, no, you're not allowed to. Seems like it really sort of understands the contract. But then I did something else. I asked him a question that is a bit odd. So I asked him, what will it cost me if I steal the car, right? Do I have to pay the entire cost? And the answer I get is, if I steal the car, yes, of course, it's bad to steal things that have consequences. But then I will have to pay up the, this thingy thing. Right? So what it shows you is, again, this notion, what you are getting are not answers to questions that are based on any sense of reasonable understanding of a thing. You're essentially getting statistics, right? Because all the other things is, if you think how it was trained, the likelihood, if you ask the question, you had a contract, the likelihood of the answer is what you got. But you don't find many texts that somebody steals a car, goes to a rental company and says, okay, I will pay this 1,500. So it's lost. Whereas anybody who has any understanding of what is happening would say, of course, you have to pay the sum if they find you. So that is really the important thing that you see here. And that's something that when you use ChatGPT, you need to understand. ChatGPT is a text generation engine, right? Is a system that transforms one text into another text, right? And it does it in such a way that if you take the input, which is your question, and the output together, the probability of that thing being a text that you would find on the internet is maximized. In this thing, it's really important to understand it's not a system that answers questions. Well, they do have a layer on it that optimizes it from question answering and stuff, but at its core, it's not a question answering question. It doesn't answer your question. It takes your question and tries to generate something where taken together, the probability distribution it had learned is satisfied. Right? Now, what happens, of course, is given that it was trained on a huge amount of text that in general makes sense, right? First of all, the probability of finding in this corpus of text that sounds bad is very low, which is why the text sounds good. Very simple. Right? The other thing is, it's not trained on nonsensical text. It's trained on text that contained information, right? So actually the probability of what is generated, be it correlated with a correct answer to his question, is fairly high. But as opposed to Google, search engine, it goes online and searches for something, right? And hits and misses. It doesn't. Right? It's this probabilistic thing that it's going to generate something that will sound good or be, highly probable, and is likely to be correlated with the answer, but not more than that. Very often it's very useful, right? And what also works very well, it's very well for summarizing things, right? Because it's this text generation engine. So I think this is really important to remember. It's not a search engine. It's not a data bank. It's not like it has knowledge, right? It certainly cannot reason in any way, right? It replicates probabilities, but then, because what it's been trained on, and I think that the important thing is, it's been trained on text that people have written. Now, why do I write text? I write text to reflect the way I perceive the world. I think about the world, right? So in this way, of course, those probabilities reflect the way people see the world, right? The world itself. So it doesn't understand, it doesn't know anything, but if properly used, it's a fantastic tool. right? I like to give this example. The step from using Google to using ChatGPT is the same as the step for many of you don't know it. And when I was finishing my master, there were still these things in libraries when you could look at films to retrieve documents, right? It's mind-boggling that science worked when using tools like that. It did, right? But the step from that to Google is essentially the same as from Google to ChatGPT. But you have to understand what it does, right? And that's really important. The other thing that's really important about this GPT, where it's foundational, is the following: is that on the way to learning how to predict the next word, it learns something else. It takes a sentence and then essentially throws the sentence and maps it into a number in highly dimensional space, right? We have 2 dimension, is actually a 500 dimension. And the interesting thing is, the way it learns is that it will map things that have similar meaning to be close to each other, right? So here, like a man, woman, king, queen, right? So we can actually compute the location of queen by essentially taking king and added to it the difference between man and a woman, right? And that is, while it suddenly becomes more than a text generation engine, which is the application, but it is a representation of a world, right? Because people have written the text to represent the way they see the world, and now it learns the probability distribution in this text and maps it into this thing, and that's sort of a representation of the world. On a philosophical level, I think it's really funny, because what happens is that it reduces 90% of the complexity of our world into just points in 500-dimensional vector space, right? So, if you ask what is the world, it's just a 500-dimensional vector space, nothing more to it, in a way. So at least that is what it's trying to say. And that is also the limitation, because it's not true, of course, right? So there's a lot of information contained in that, but that is the way. And it's the representation. And, that is, for me, the main really thing about machine learning is about representations of knowledge, right? As I said, you can just use this 2-dimensional 2-layer neural network to do everything. You would never finish. So the difficulty of building machine learning system is the difficulty on finding representation. And you know that, right? You look at the heliocentric and geocentric representations. Idiotic people were burning each other about it, but in the end, it doesn't really matter. Both is true, right? It's just a different representation. You go into geocentric system, representing planet orbits just becomes crazily difficult. It's not, none of them is wrong or right. It's just a representation, right? But the right representation can make a difficult problem very easy. And that is what really machine learning is. If you remember that thing, that you understood what all this machine learning thing is about, finding representations that make finding stuff easy, right? And then again, data encoding is something like a word representation. And of course, once you decide that you can have this representation where, man, woman, king, queen have this relationship, generating that should not be something that is restricted to text, right? It should be, no matter in which way you input the information, you can get the same representation. And that's something that really enables all these vision systems. So essentially what people do is, people said, okay, I take the text, I do this mapping into this funny space that brings similar things together, and then I take pictures and try to develop a system, again, with a proper loss function, that will map images that contain a queen and a king onto the same points in the space, right? And once you have that, you essentially are done with systems that explain pictures, that create pictures. Because what you do, I have a picture, I want an explanation in text. I take the picture, I use my system to map it into the point in my space, and I take the system that takes the point in the space and generate text. And now I have a system that describes what is in this picture. I want to generate a picture, I reverse it. I write the text, I have my neural network, again, just vector matrix multiplication, it maps it into this point in space. I take the other networks that take points in space and maps them into pictures. Right? So these things that you think, wow, these things understand text and can create pictures, it essentially all works through this representation in the space that has been trained using the stuff. Other thing you can do with it is something that people also have been saying is like a magic property of new AI, which called like a zero-shot learning. What happens is you have a system that has never ever been trained to recognize, I don't know, dogs or cats. What you do is you just essentially say, things I want to distinguish here are plane, car, dog, and bird, right? And what happens is this thing can map it into these points in space. Now just start in pictures, right? They are mapping the point in space. I look what is closer to this point. Is it the text for cat or a text for dog? And this way the system essentially can do things it was never explicitly trained to do, right? By using that representation. That is the power of this and that's why it goes generative AI, right? It talks not because you have the space, and then from the space you can generate all sorts of stuff. Okay, so there was a quick summary of how these things work. Again, it's a very simple principle, but I think it helps to have this understanding what is happening to then understand what you can expect it to do and not to do. Right? So this mapping, all about loss function. It's got nothing to do, with intelligence in a human sense, which is the problem. I don't know if anybody can define what this intelligence is. So it's a set of mathematical methods that use numerical optimization to train, parameters function with a loss function into this sort of mappings, and then to switch between mappings, and that's what it does. Now, what are the limits of the system? And that's quite interesting. So first of all, we had this classification problem. What you would look at, you have like 2 dimensions. These are points that belong to one class. These are points that belong to the other class. This was like an example on how you could classify cars for different customers, but this could be the fish, or it could be face recognition, right? So the minuses are the one class you want to see, the bad one. The pluses are a good one, right? So how can I define and find here this function, this separates it? Now imagine you have this, divine insight, and you know that the actual separation is this one, right? It's something that you do not know, but that is the truth. So anything that falls within this blue square is plus, anything outside is minus. So you do machine learning, right? You are clever enough to understand that my function that separates this is a square, and then you do numerical optimization to find a square that essentially will perfectly separates the points in your sample, which means you find a square where all the minuses in your sample are on the outside and all the pluses are inside. You see something, that yellow square is not the same as the blue truth. And the funny thing is, of course, you did nothing wrong, right? You found the right hypothesis, so essentially you identified the right function, which is a square, and you had no noise in your data, and you perfectly estimated the parameter, and your answer is still wrong. It's not totally wrong, right? But anything that falls into this or this area will be classified wrongly, right? And that's something that is very fundamental limit. You call it, that you can make a square that is closer to your pluses. You can make a square that is closer to your minuses. One is the most special, one is the most general hypothesis. And in between, you have space for which your data tells you nothing what to do, right? And that is a fundamental limit of the accuracy of machine learning systems, all of them. Again, the point is, your data is perfect, everything you did is absolutely perfect, and your system still makes errors. Why? Because system is just based on samples and statistics, right? So there's one very simple way to make this thing perfect and make the error go away. Any idea how? Very simple. You just need infinite data, right? You have infinite data, you don't make errors. And so machine learning is exact in the limit of infinite data. And the funny thing is, we have it quite often. We talk to people, for example, from industry, and they say, we have the systems that work perfectly, but now there's artificial intelligence, machine learning. Let's try to find a machine learning intelligent system that works, because intelligence is better. And that's total nonsense, right? Because actually, this machine learning model is worse than an exact model, because it's based on statistics, it had inherent errors. And then, of course, you have other errors. Like that's something that's very, very well known and very common. This was the thing people trained, for example, a system to recognize different type of dogs, huskies versus wolves. Very difficult problem. I would not do it. Working very well until people find out that in one place it was classifying actually a husky as a wolf. And they find out that the reason it was so was that in the training set, all the dogs, all the huskies were on green background, and all the wolf picture were on snow. So the system just learned to distinguish snow from grass, right? Like a cheating student. And it comes back to this notion of using your loss function as your programming. You defined the wrong loss function. You didn't do the loss function that distinguished animals, it distinguished the pictures, right? So that really is very important. And that is where these things like, there's a lot to talk about, gender and bias in AI, right? It's not like AI is somehow biased or discriminatory, whatever, right? It just like with green grass and the background, it's trained on some data, and if it's supposed to say something, it just goes back to the data it has seen, right? So, this typical thing that men in completed photos will be wearing suits, women mostly bikinis, things like there were photos that generated of black people predominantly with arms. It's just essentially, providing you in a mirror, reflecting what is there. But then, of course, it doesn't say it's good, right? Because once you have this mirror, once you use that for things that impact people's lives, it actually can be very dangerous. But it's not like the AI itself is evil. It's just trained on data, and it tends to enhance the bias that you would find in everyday lives. So it's also important where it comes from. There's other sources of errors. It's something that's called adversarial attacks. If you look at something like this, is a stop sign. Then you add to this image this sort of a noise, right? And you get something that to a human still looks like a stop sign. But the system interprets it completely differently. And the reason it does so is, again, because it was not trained to really understand stop, but somehow with this very, very complex separation boundary in this n-dimensional space, right? This arrows that you have, the boxes. The point was that the stop sign with that noise just fell outside the boundary. It's a very, very different representation. So here's another thing that you have. I was actually, when we were writing our proposal, I used this thing, to generate different type of landscapes. So I said, generate me, a picture of a neighborhood with a church in the background. Actually, it looks pretty good, right? It looks like standard things. One thing I noticed, if you actually ask it to generate a mosque in the background, you get a more shabby neighborhood. Typically, that's another thing that you would be getting. But then I asked it to replace the mosque, the church tower with a chimney, factory chimney. So that works really well. And here's another example it generated that actually has a cross on top of a chimney. Now, and that's another example of this thing not understanding anything, right? You could make many mistakes. I would draw it very badly. But you would never draw, and it's not even the same cross. It's not even like it kept the cross, right? It generated a new one. So that shows the system has really no model of all that's underlying the data. It just replicates some statistics, and in that statistics, having that cross on top somehow was not enough to tip the error function in a different direction. So again, in summary, we said that anything computed, why do you do machine learning if it's that bad? The really big thing about machine learning is that it actually allows you to program the computer to do something that you yourself do not know how to do. It's not that a computer does something it was not programmed to do, but you have no clue how to solve a problem. But what you do is you know how to specify what is a good solution as what a bad solution. You can write it at your loss function, and you know where data is that can actually help the system find that solution. Right? So that is why it's really, really good. It allows you to do things you would not be able to do, but there's a price to pay. There's no such thing as a free lunch, right? So first of all, it's an approximation. And the other thing is, in general, you have no clue what the system will do. And why is that? Because the reason you actually use the system to extract the solution from the data is because the data is so huge and so complex that you cannot analyze it. If you could, you wouldn't need a machine learning program. And then if you cannot analyze it yourself, you just give it a computer, it extracts the parameter values and the answer, then you have no clue what it will do. It follows your loss function, but if the loss function is not perfect, it will do something wrong, right? So one thing that people very often say about machine learning, which sort of makes me crazy, is they say, it's a very different art of system because they can go beyond programming. Of course they cannot go beyond programming, right? You program them to go there, take the data, do numerical optimization to satisfy a certain loss function. They do nothing more. And then they take the function they computed and use it. But it's a fairy tale, right? But like every fairy tale, there's this small truth in the fairy tale. And the truth there, of course, is what I said before. You have this huge amount of data, right? You define the loss function. And what you can say is that system came up with the answer that satisfies the loss function, but you don't know what it will do because it's so complex. So it's not that like the system does something it wants because it becomes whatever, conscious or whatever nonsense, but it does things that you will not foresee it will do, right? And that is something about intelligence also. I like to always show this quote from my favorite science fiction writer, Arthur C. Clarke, who once said, any technology that is advanced enough is indistinguishable from magic. That is sort of true. It's always been. Show a jumbo jet taking off to somebody from the Middle Ages, right? They'll be say this is some sort of a beast from hell that will eat us alive, whatever. And in a way, that's true for this machine learning, right? Any analysis that is advanced enough on a sufficiently a large amount of data looks like intelligence, but it's not, right? It's just numerical analysis, right? And I think this is something that you need to really understand. And the same goes for this whole discussion that we've had about the danger of those large language models somehow making humanity obsolete and taking over the world, right? It's a fantastic publicity, right? It's very nice to generate publicity, go into press and do stuff, but it's of course just a fairy tale. It's utter nonsense. And people like Elon Musk use it very consciously, essentially, to generate exactly this, to generate publicity. But again, like with any fairy tale, there is this grain of truth in it. Because if you look at this thing of you not being able to understand what a system may do, and if you look at the number of critical systems that are now being controlled by AI, financial systems, traffic systems, energy systems, right, credit rating, you follow computer recommendation when you navigate, when you do stuff. And those things partially control critical systems. And you give control of critical systems to devices for which you have no clue what they will do when. Right? And even millions of them controlling all sort of stuff. And that is something that actually can be dangerous, right? Not because this AI will just vector matrix multiplication wakes up, and decides I'm Genghis Khan and takes over the world. It's nonsense, right? But if you have sufficient number of things that just you don't know what they're doing, it's going to do a problem. So my point is, it's not artificial intelligence being too intelligent that can kill us. It's artificial stupidity, right? So you have to make sure that you use system for purposes they are good for. And there's something we just wrote an article as applied to this stupid discussion about pausing research on large language models and stuff. And Holger Holz, a colleague of mine, really did a very nice quote here, right? So the real problem with those generative AI systems is not that they are too powerful, they are like AGI is artificial general intelligence. The problem with those systems is that people hopelessly overestimate what they can do and tend to use them for things they're absolutely not suitable for, right? People... And it's very clear why they do so, right? Because you ask ChatGPT something, you get the answer that sounds like being generated by some really intelligent, knowledgeable human being. And that appearance, right, tends to lead you to believe that there is something comparable to a human being on the other side, not just some statistics. And that is really the danger, right? So again, the danger is the combination of natural and artificial stupidity taken together. Right, that you have here. And that is also for your research, when you use those things, always understand those are extremely powerful statistical tools that have an approximation of a world model, that are fantastic text manipulation engine that can manipulate and map content of pictures to content of texts, but that's all they are, right? That there's no understanding, that there's no reasoning behind it. It's just like, you use R, I think that's what you use in social science, R and tools like that, to statistically analyze data. And it's like a R, or I like to even tell, AI at the end of the day is just a pocket calculator on steroids, on a lot of steroids, right? On steroids and many, many other things. But that's it, right? And that's what I also like to talk about, ethics of AI. It's one of my nice slides. Well, I like to show, Spider-Man, like science fiction movies. So there's this very nice quote in Spider-Man saying, "With great power comes great responsibility," right? And that's sort of the way to approach AI. AI is hugely powerful, so we need to use it responsibly. But it's neither good, it's not bad. It's certainly not something that takes over the world. It's not something that will make you happy for the rest of your life. It's just a calculator on steroids and many other things. Thank you. Yeah.
Yes. Thank you for this very nice speech. You know that I always learn a lot from your speeches. And my question is for the more naive social scientists in the room here, and not so much for the computer science data scientists. What would you, if you were like a social scientist like me, use the pocket calculator on Generative 4 in my research. I know that you use and play a lot with all those machines, but you can estimate the risks you take and the problems. What would you use them for if you were me?
So there are two things. First of all, it's actually text generation. Mm-hmm. Although it's something that may be difficult. I think that's what Passant mentioned in terms of sort of ethics, research ethics, right? So in our field, I tell students, before you write a bad text, just use the thing to generate proper text, right? But of course, the problem is that the quality of text is not in any way a criterion for your scientific work, right? What you have is you have hard facts, and it's just a way of explaining it. I know that in some social science areas, it's not about the content, it's about the way you present the content, right? Very strongly, a different point of view, which then, of course, may become problematic if instead of, you just write bullets and let ChatGPT generate it. So that is an issue. But in case, if you have something where it's all about actually generating, especially in a foreign language, nice-sounding text, just use it, right? It can write text better than you can. The other thing that you can use it for is actually, analysis, for example, trying to extract, I don't know knowledge, but extract things from text, right? So, or even asking, if you ask it a question, in a way, right? If you give you an answer that represents, what has been there on the network, you give it a text and try to ask it to summarize the text. It can do that very well, right? So if you want to do something like analysis, for example, of documents that people have written or statements that people have written, I think the only thing that you have to remember when you use it that is critical is that you have to take the answer with a big grain of salt, right? It means, so I had this discussion, and my younger son, he's 12, and he had some research to do, and I just came, here's Copilot on your phone, use it, right? But the reason I asked him to use, for example, Copilot on not ChatGPT is that actually Copilot on your phones shows you the list of sources. So essentially it generates this text, but tries to find places on the internet. They are not perfect, right? But you get the answer, and then you go to the sources and you verify it, right? So I think it's a long answer to a simple question, but it's not easy. But my answer would be, use it for anything you think may be useful. Just, there's no limits to your fancy. Understanding that it doesn't generate knowledge, right? It just extracts knowledge. And then always check, because as opposed to running R or something, or as opposed to doing Google search, you never know. So typically you put it there, it's a very good starting point. I just talked to somebody here in quantum physics. They're doing a paper. They asked the system to write in Python code, actually, to verify the paper. But you don't just run the Python code and trust it. You take it and you look at it. It's still faster than writing it by hand. So verify. Yeah?
Next question. Yes.
Thank you very much for the presentation. On your opinion, I have a question about AGI. On your opinion, could we create AGI relying on this stepwise approach which you presented, or we need something completely new, some completely new technology approach or paradigm to create this AGI?
There are numbers of difficult. First of all, I don't think that anybody agrees with what actual AGI is, as much as people don't agree with intelligence is. But I think eventually people, for me, life and world is just physics, right? So if you have this point of view, then obviously our brains are just some sort of biological machines. So what we can do, eventually we must be able to replicate in a computer. So eventually we will be able to create something like an AGI. It's just that if you look at the way current technology is, it's just not a way to get there, right? I mean, there is one philosophical twist to it. Some people say, yeah, you're completely right. All this thing do is vector matrix multiplication. But then what is the guarantee that your brain does anything more, right? So that is an argument you can make, right? But for example, GPT is very definitely not an AGI. It's a statistical parrot. But eventually, it's an interesting question. That's why those discussions, the discussions about the ethical aspect of creating an AGI, of creating a conscious computer, are things that I think really interesting on a philosophical level, because eventually we will come to that stage where that may become relevant. It's just that saying that GPT, just because it can create things that sound nicely, has anything to do with the AGI, is just publicity stunt.
Questions? Further
I
questions?
have a follow-up on this question.
Okay.
The Vice President of AI at Meta is continuously saying that we have to completely change the way we are training these models and give these data in another way to create the AGI. We can't do it with the current way of training, like the linear regression is the core of everything we have now of training. So we have to change the way of training, and no one has did a different way of training right now.
To put it in other words, I like to put it provocatively, is the probability of ChatGPT becoming conscious is exactly the same as probability of my toaster becoming conscious. It's the technology is just
Make a good statement on AI on demand. Keep talking.
but that's actually true, and I really believe that it's an issue that may be, but it's just a technology that doesn't have a path unless you assume that our human brain is nothing more than a vector matrix multiplication, which may be, right? If you have an assumption that there is more to that, then that statement is true. Yeah?
But that's rather an architectural choice, isn't it? That it's not possible to be conscious because it's strictly feed forward. So if you would insert other units that could process previous context, it could be something that resembles conscience.
You don't change the fundamental principle. It stays a vector matrix multiplication. You do have the recurrent neural networks. Much of the stuff are state of the art, right? Transformers, in a way, what you have is recurrent. It doesn't change the principle. Right? It doesn't change anything. It just changes the complexity of what you can work on. Right? And what you do is a recurrent neural network you train using loss functions and numerical optimization. It's just the thing. If you write code, I used to do it as a student. I was sort of a hacker, and it's if you write like self-modifying code, right? It's the same thing. In the end, you have no clue what the bloody thing will do because of the self-modification. But it still doesn't change that it's just code. At the end, you run it in the computer. It's just a Turing machine. This thing is as long as you can run the code on this device, it remains a Turing machine.
I rather meant that it doesn't necessarily have to be strictly code. If you insert central processing unit components like memory and all of that, it could have a different artificial experience than just always generally predicting the next word. It could rather update, as you said, self-updating code and stuff. It's a broader space of possibilities if you consider different architectures, I would say.
I would disagree. It just makes it
more. We should
more.
talk about that later, though.
Yeah.
I think right now.
But I don't deny that there certainly should exist a path to replicating what a brain does. It just doesn't seem what just is beyond discussion, but it just is a fact that no matter how you create current neural networks, it remains something that you can describe to vector matrix multiplication of finite matrices, and learning is just numerical optimization. If you think you can achieve consciousness and intelligence using that is difficult to argue with.